let's have a look at number 27. We've got this graph, which is displaying the height of a rocket in feet over time, which is measured in seconds. So part A, how high off the ground is the rocket after 15 seconds? 15 seconds is right here, and if we look at the y-coordinate, looks like that's 250. So 27A, 250 feet. 27B, at approximately what time is the rocket 200 feet above the ground? So I just look at 200 feet and I ask, when does that occur? Looks like 2 times. Once at 10 seconds and again at 60 seconds. So 10 seconds and 60 seconds. 27C, what time does the rocket reach its greatest height? That occurs, looks like right here, and the time at which that occurs is 30 seconds. And then 27D, what is that greatest height? So there's a difference between asking when does the greatest height occur, which is the x-coordinate, 30 seconds, and what is that greatest height, which is asking the y-coordinate, which is 300 feet. 27E, after how many seconds did it hit the ground? Well, hitting the ground means that you are 0 feet above the ground. So that would be here. So it looks like 72 seconds or something like that. You sort of have to approximate. Okay, 27F. Over what time interval is the rocket rising? So that's when the graph is going up, which would be from 0 to, so it's the time interval t between 0 and 30. 27G, over approximately what time interval is the rocket dropping? That's from 30 seconds in to the end, 72. So I'd say like 30, t between 30 and 72. H, how high did the rocket rise in the first 5 seconds of flight? Well, from 0 to 5, looks like it goes up to here, which is 120, I think, because I think these are increments of 10, 10, 20, 30. Yeah, so 120. 27I, you just found how far it rose in the first 5 seconds. Divide your answer by 5 to find its average velocity in the first 5 seconds of flight. Maybe I'll say a couple things about this. Average velocity is basically the distance that you travel divided by the amount of time that it took. During the time interval in question, the rocket rose by 120 feet, and it took 5 seconds for that to occur. So that's 120 over 5, which I think is 24. So that's 24, and the units are feet per second. 27J, from t equals 10 to 30, how many feet did the rocket rise? Over how much time? And then what was the average velocity from time 10 to 30? So let's go through that. So at time 10, looks like it's here at 200. And then at time 30, looks like it's here at 300. So from 200 to 300, that's 100 feet is how far it went. And how much time elapsed? Obviously 20 seconds. And so the average velocity, again, that's just the distance over time. That's 100 feet divided by 20 seconds. 100 over 20, that's 5. And the units are feet per second. I kind of want to double check that I did that right. That's pretty small. Did I mess something up? So from 10 to 30. So time 10, you're at 200 feet. And then at time 30, you're at 300 feet. So you're up 100 feet over 20 seconds. No, that's right. That's right. Okay. Okay, find its average velocity from time 30 to 45. Yeah, so you're seeing there's a lot of stuff around average velocity. So from 30 to 45. I think maybe it would be worth at this point introducing an equation for the average rate of change. If you have some function f of x, or I guess in this case our variable is t, so maybe I'll say f of t. If you have some function f of t and you want to know the average rate of change of the function f of t from time t equals, let's say, a to time t equals b, there's a formula for that, and that's the formula that we've implicitly been using, maybe without knowing it, in the previous problems I and j. Oh, not average rate of change, average rate of change. And the formula for the average rate of change from time a to time b is f of b minus f of a over b minus a. You'll see this later in the worksheet. So that numerator is basically how much the function changed, and the denominator is how much the variable changed. In this particular problem, the function f that we're thinking about is the height, and the variable is time t. So in number k, we're thinking about the average velocity, that's the average rate of change of the height from time 30 to 45. So notice in the numerator, it's like the later value of the function minus the earlier value of the function. So that would be like the height at time 45 minus the height at time 30 divided by 45 minus 30. The height at time 45 is here, which is that, what is that, 270? Yeah, 60, no, 280. That's 280. Right, so 280 minus the time at 30, which is 300, over 45 minus 30 is 15. And so you'll notice that that gives you a negative value. That's negative 20 over 15, which can be reduced. That's negative 4 over 3, and the units once again are feet per second. And so I just say all of that because I want to emphasize that average rates of change, or in this case that means average velocity, they can be negative. If your function is decreasing over this time interval from time a to time b, then this formula that I'm using here will produce a negative result because the numerator will be negative. So it's perfectly ordinary to have a negative velocity or a negative average rate of change. That basically indicates that whatever function you're looking at, in this case the height function, is actually decreasing. So that's what's going on there with the negative result. Okay, so that brings us to 28, maximum and minimum values. So this is the difference between relative and absolute. So relative maximum occurs when a function switches from increasing to decreasing. That's a little bit of a complicated definition. A relative maximum is basically just the top of a hill. So if you look right here, that's the top of a hill. But if you'll notice, that actually does match the definition we give you. That's the location at which the function switches from increasing to decreasing, because at first it's increasing, and then at that moment it switches to decreasing. So yeah, this function has a relative maximum at x equals 4, certainly. And 28b, it says a relative minimum occurs when the function switches from decreasing to increasing. Another way of describing that is a relative minimum is just the bottom of a valley. So like right here would be the bottom of a valley, but again, if you notice, that does match the definition we're giving. It's a place where the function switches from decreasing to increasing. So I'd say there's a relative minimum here. There's also one over here. So there are two of them. One of them at x equals 1 and another one at x equals 9. 28c, the absolute maximum and absolute minimum values are literally the biggest and smallest y values. They can occur at a relative maximum or minimum, and then it says somewhat cryptically they may occur somewhere else, or they may not occur at all. Let me just say another couple words about that. We'll talk about this more in the course, but roughly speaking, a relative minimum or a relative maximum, like a relative maximum is the biggest value locally. Like this guy is kind of the biggest value in the neighborhood, but it's not the biggest value, the biggest y value in the entire universe. That occurs over here, right? So this guy is the absolute maximum, whereas this guy is only a relative maximum. So in this case, the relative maximum here is not, sorry, the absolute maximum here is not a relative maximum in our definition because like it's a boundary point. What I'm getting at is absolute maximums and absolute minimums. They occur either at relative maximums, relative minimums, or they occur at boundary points, which is what this guy is. Anyway, so the absolute maximum value occurs when x is equal to 11, and the actual maximum value itself is 2, right? And then same question for the absolute minimum. The absolute minimum occurs here. That's when x is equal to 9, and the y value at that moment is -8. So I would say, to be clear about the language, I would say that the absolute minimum itself is -8, and it occurs at this moment in time. Okay, we want to distinguish between what the absolute minimum value is. We want to distinguish that from the time at which it occurs. So average rate of change, I talked about this a little bit before. This is our formula, f of b minus f of a divided by b minus a. This quantity will be negative, as I said earlier, anytime the function is decreasing. Let's have a look at 29, which just asks us to practice the average rate of change formula. So our formula here that I'll be using throughout is f of b minus f of a over b minus a. That's the average rate of change, which we often abbreviate as AROC, over the interval a to b. So b is the later time value and a is the earlier time value, to be clear. So we're being asked to find the average rate of change of this function on each of these intervals. It's nothing more than plugging in these values for a and b into the formula. So in this first example, a 7 is the a value and 11 is the b value. So for the first one, that's going to be f of 11 minus f of 7 over 11 minus 7. F of 11 would be, that looks like 6. So I think that's 6 minus f of 7 is 0. Over 11 minus 7, that's 4. So 6 over 4, that's 3 over 2 or 1.5, whatever. Okay, and then we have average rate of change over 13 to 16, same idea. So that's f of 16 minus f of 13 over 16 minus 13. It's really just the amount by which the function changes divided by the amount by which the variable changes. So f of 16, that would be 3, I think. And then f of 13, that would be 7. Over 16 minus 13, that's 3. So that's -4 over 3. And again, average rate of change will be negative anytime the function is decreasing, as it is, over the interval in question. And then finally, average rate of change over 13 to 18. This is just more of the same. Not really sure why we ask you to do this many times. But, so that's f of 18 minus f of 13 divided by 18 minus 13. F of 18 looks like that is -5. And then f of 13 looks like that's 7 over 18 minus 13, that's 5. So that's -12 over 5. Voila. Okay, 30, consider the function f of x equals x squared minus 4x. In part A, we're finding f of 8 and f of 5. That's easy enough. That just means plug in 8 for x. So that's 8 squared minus 4 times 8. So that's 64 minus 32, which is 32. And then likewise, f of 5, that would be 5 squared minus 4 times 5. That's 25 minus 20, which is 5. 30b is asking us to find the average rate of change of the function over the interval 5 to 8. We've already done some of the annoying work. That would be f of 8 minus f of 5 over 8 minus 5. We already computed those values earlier. So that's 32 minus 5 over 8 minus 5 is 3. So that's 27 over 3, which is 9. Okay, C, we should have gotten 9. We did. That's great. Now find the average rate of change over the interval 1 to 9. This is a bit repetitive, but you're going to compute the average rate of change in like a million different situations. So it's kind of something that just needs to be second nature. Like you just want to have a muscle memory for it. I think that's why we're asking you to do it so many times. So average rate of change from 1 to 9, that's going to be f of 9 minus f of 1 over 9 minus 1. The denominator is 8. The numerator, what's f of 9? That's 9 squared minus 4 times 9 minus, now I'm going to do something interesting. I'm going to put the next expression in parentheses. Okay, so this is going to be f of 1. F of 1 is 1 squared minus 4 times 1. And notice I've enclosed that expression in parentheses, or actually brackets. Doesn't matter, same thing, just a choice of style. But I enclosed that expression in brackets because I'm supposed to be subtracting f of 1. In other words, I should be subtracting this entire expression. So this minus sign should be applied to this entire expression, and without those parentheses, that won't happen. So I'm just using those parentheses to make sure that I correctly subtract all of f of 1. So 9 squared, that's 81, minus 4 times 9 is 36, minus, let's figure out what that thing is in brackets. It's really just 1 minus 4, isn't it? So that's negative 3. So be careful with your double negatives here. 81 minus 36. What is that? Is that 45? I think that's 45. Yep. And then minus negative 3 is like plus 3. So it's 48 over 8, which is 6. Cool. And then finally 30D. So same thing, but again, we're going to do it over yet another interval. So that would be f of negative 3 minus f of negative 5 over negative 3 minus negative 5. So a lot of like double negatives and stuff happening here. So f of negative 3, that's negative 3 squared minus 4 times negative 3 minus, and again, I'm going to enclose all of f of negative 5 in parentheses to make sure that I subtract the entire expression, not just part of it. So f of negative 5, that's negative 5 squared minus 4 times negative 5. All over negative 3 minus negative 5, that's like negative 3 plus 5. So simplifying negative 3 squared, that's 9. And then we have minus 4 times negative 3, 4 times, that's like plus 12, right? Minus, and then what is that expression in brackets? It's 25 minus 4 times minus 5 is positive 20. Negative 3 plus 5 is 2. So 29 plus 12 is 21. Minus, and then 25 plus 20 is 45 all over 2. So I think you get negative 24 over 2, so negative 12. Hopefully I did that right. Cool, cool. Moving on, so now we're going to talk about average versus instantaneous velocity, just to give a little bit more commentary about what it is we're up to in this problem. There's actually two different notions of velocity, and this is not something that we typically think much about, but it's one of the central themes of the course. When you get into your car and you drive around, your speedometer is measuring your speed or your velocity, roughly the same thing. But I want to emphasize that what your speedometer is measuring is actually not any kind of average velocity, right? Average velocity is computed by taking the total distance that you traveled over an interval of time, over some span or period of time, and then dividing by the length of time. So, you went 106, if you go 120 miles over the course of 2 hours, well, that's an average velocity of 60 miles per hour. But of course, in a car trip, you probably, didn't go exactly 60 miles per hour the entire time. Like your speedometer was probably not reading 60 miles per hour the entire time, right? The 60 miles per hour figure is an average. It's how fast you were going on average. That's fine, but then you have to ask yourself, like, okay, well, if the speedometer isn't measuring average velocity, what is it measuring? It's measuring something else called the instantaneous velocity. And instantaneous velocity is a little bit more of a subtle concept. And as we'll see, it actually requires limits to understand in a rigorous mathematical way. But the long and short of it is that, as we'll be seeing in these problems, basically what we're up to is we're trying to convey to you this notion that the instantaneous velocity, which is the velocity that your speedometer measures in your car, the velocity that you're traveling at one instant in time, not over a span of time, not over a period of time, but the rate at which you're traveling at an instant of time, that instantaneous velocity can be approximated. It can be approximated by computing average velocities, which sort of surround the instant in question. So that's a bit of context about what we're talking about in this series of exercises, if you want it. So let's read these problems. So Pedro the caterpillar went for a walk. His distance from home is graphed to the right. The grids are in 0.2 increments. Cool. Suppose we wanted to know how fast he was traveling exactly 3 minutes into the trip. In other words, we're saying, let's suppose we want to know what is the instantaneous velocity 3 minutes into the trip. Like, what is Pedro's speedometer reading 3 minutes into the trip? That's not an average velocity computed over some span of time. That's a velocity that is thinking about how fast you're going at one particular instant. And so what we're going to do is we're going to approximate that unknown number by looking at average velocities near 3. All right. So I'm going to jump directly to this question here. Estimate his average velocity from 1 minute to 5 minutes. So we're going to look at the average velocity from 1 to 5. That would be f of 5 minus f of 1 over 5 minus 1. That's the average rate of change formula. So f of 5, that's simply his position at time 5, which it looks like it's... so these are increments of 2. Here's 7. So 7.2, I don't know, 7.3 or something. So 7.3 minus f of 1, which looks like it's like 3.9 probably, divided by 4. So what is that? 7.3 minus 3.9, that's 3.4. So 3.4 divided by 4, it's like 0.85. What are the units? Do we know the units here? Well, I know that the time is measured in minutes. Oh, and then, this says time in feet. That's obviously supposed to be distance. Anyway, it's feet per minute, right? So that's the average velocity from 1 to 5, all right? The idea that you should have in mind is that this interval, 1 to 5, is an interval of time containing 3 minutes, right? Like if you think about the interval 1 to 5, time 3 is smack dab in the middle of that time interval, okay? And the idea that we want to convey to you here is that if you compute the average rate of change over an interval containing 3 minutes, what you get is an approximation, an estimation of the instantaneous velocity at 3 minutes, okay? The other idea that we want to convey to you is that the smaller you make this interval, the better the approximation becomes. So that's 31A. 31B, we're doing exactly the same thing, but what we're going to do is we're going to shrink the interval. Now we're going to look at the average velocity from time 2 minutes to 4 minutes. So that's the interval 1 to 4. Once again, 3 is right in the middle of that interval. So whatever this number is, whatever the average velocity is from 1 to 4, that's going to be, or sorry, I typed 1 here, I meant 2. So once again, 3 is right in the middle of this interval. So whatever we get here as the average velocity is going to be an approximation of the instantaneous velocity. It's going to be an estimate of what Pedro's speedometer was reading at this time. So that's going to be f of 4 minus f of 2 over 4 minus 2. F of 4 is, looks like it's 7.1 minus f of 2 is 4.1. 4 over 4 minus 2 is 2. So that's 3 over 2, which is 1.5 feet per minute, which is quite different from this average velocity, right? But I'm telling you that this number here is a better estimate of Pedro's instantaneous velocity at time 3 than this guy is here. And if you want an even better estimate of the instantaneous velocity at time 3, then you should consider the average velocity over an even smaller interval, which is what we're going to do next. So average velocity from 2.6 to 3.4, that's even smaller. So now we're considering the interval of time 2.6 to 3.4. Once again, 3 is right in the middle of that interval. If I look at f of 3.4 minus f of 2.6 over 3.4 minus 2.6, what is that? So f of 3.4, that's this guy here. Looks like that's 5.8. I'm bound to mess some of these up at some point or another, but hopefully I don't. F of 2.6, that would be this guy here. So f of 2.6 looks like that's about 4.4, I think, right? Over 3.4 minus 2.6, that's 1.2. So what is that? 5.8 minus 4.4 divided by 1.2. It's like 1.16. That's again feet per minute. So that's an even smaller interval than the previous two. This is probably a pretty good estimate of how fast Pedro was actually going at exactly 3 minutes. In other words, it's a pretty good estimate of his instantaneous velocity at that time. Okay, I guess we're doing one more, a little bit repetitive, but it's worth doing this at least once. So average velocity this time on a very short time interval from 2.8 to 3.2. So now we're considering the time interval 2.8 to 3.2. And once again, notice that 3 is right in the middle of that interval. The average velocity over that time interval is f of 3.2 minus f of 2.8 over 3.2 minus 2.8. Let's look at the graph. 3.2, I think that's right here. I think that's going to be 5.4. F of 2.8, I think that's right here. So what is that? I think that's 4.7. Over 3.2 minus 2.8 is 0.4. So what is that? So 5.4 minus 4.7 divided by 0.4 is 1.75. I kind of feel like I probably messed this one up. Let me double check this real quick. F of 3.4. That's 5.8. Yeah. F of 2.6. That's 4.4. Yep. Over, 3.4 minus 2.6. Yeah, that's not 1.2, is it? That is 0.8. Yep, my bad. Sorry about that. So 5.8 minus 4.4 divided by 0.8 is 1.75. Interesting. Got almost the same thing. I got exactly the same thing as I did here. So really quick, like, why do you think I went back to this one under the suspicion that it was wrong? The idea is that as you shrink the interval containing 3 and compute the average velocity over the interval each time, what you're doing is you're getting a better and better estimate of the true instantaneous velocity at time 3. That means that this sequence of numbers shouldn't be like jumping around randomly. It should actually sort of be converging towards something. It's unusual for these two numbers to be exactly the same. That's kind of a coincidence. However, this sequence of values, as you shrink the interval, should be getting closer and closer to the true value of the instantaneous velocity. And this value, which I had computed incorrectly earlier, was not following that pattern, right? Like it was like 0.85, 1.5, and then some random stupid number, and then 1.75. And I was like, that really doesn't fit the sequence. Let me go back and double check that. So that's how I knew. Okay, but as you can see, as you shrink the interval, this sequence of average velocities seems to be zeroing in on like 1.75. So the true instantaneous velocity at 3 seconds is probably around 1.75. Okay? Yeah, so the answer to D is probably 1.75. Of course, you might wonder, like, how do you know for sure? Well, the thing is, we can't know for sure only given this graph because we're kind of estimating the y values, you know what I mean? Like when I look at the grid and I figure out a y value, a lot of the time I'm kind of just making my best guess about what the y coordinate of the graph is. So if you only have a graph, then the best that you can do is estimate instantaneous velocity. You can't really find it precisely. And there's kind of a limit to how accurate you can be because, you know, you can only zoom into the graph so much, you know what I mean? After a certain point, it just becomes all pixels. We'll show you in the course how to find average velocities precisely. It involves limits, as you might imagine. Like you're essentially, you need to take the limit as the size of the interval shrinks to 0. So anyway, so what is this problem about? In the last problem, we used a symmetric interval around x equals 3 to estimate the exact velocity or instantaneous rate of change. We actually don't need to have a symmetric interval to do this. For this problem, consider the function f of x equals x cubed. I recommend using a calculator. Cool. I'm gonna use Desmos, actually, because it's gonna take way less time. So I'm going to be using the function f of x equals x cubed. So I'm just going to type that in. Notice, by the way, when I use Desmos, I don't just type y equals x cubed. You should give it a name because that allows you to like compute with that function really quickly. Like if I want to know what is f of 2, I can just type f of 2. There it is. If I want to know f of 1.9, that's f of 1.9. Okay. Yeah, so let's compute just really quickly. Let's compute. I want to make sure the problem that I'm working on is sort of displayed on the screen here. Let's compute in 32a the average rate of change of this function, f of x cubed, over the following sequence of intervals. So average rate of change from 1.9 to 2, that would be f of 2 minus f of 1.9 over 2 minus 1.9, and I get 11.41. So, you know, we're approximating the instantaneous rate of change at 2, okay? And this interval, 1.9 to 2, that interval contains 2. The point that we're making in this problem is, unlike the example with the caterpillar, the previous problem, the time at which we're estimating the instantaneous velocity, 2, is not in the middle of this interval, right? The middle of this interval, the midpoint of this interval, is 1.95. What we're trying to convey here is that doesn't matter. The value, all that needs to happen is that the time at which you're trying to estimate the instantaneous velocity, 2 in this case, needs to be on the interval. That's it. Okay, like it needs to be on the interval, and that's really all that matters. Okay, so as long as 2 is inside this interval, and it is, the average rate of change over that interval will be a valid estimate of the instantaneous rate of change at 2. 2 does not have to be in the middle. Okay. Anyway, f of the second interval, so f of 2 minus f of 1.99 over 2 minus 1.99, that's 11.9401, a little bit different from this answer. And now here we've got a really small interval, right? Really, really small. And look at that, 11.994. Look at this sequence of numbers, 11.41, 11.94, 11.994. That sequence of numbers is not jumping around randomly, but rather converging, getting closer and closer to some value. It looks like it's getting closer and closer to 12. If you wanted to convince yourself, that it really is, well, make the interval even smaller. Like change this to 1.9999. Oh, look at that. It's even closer to 12, right? So as I shrink the interval closer and closer to 0, the average rate of change gets closer and closer to the true instantaneous rate of change, which is almost certainly just 12. 32b, we're doing exactly the same thing, but now we're computing using intervals where 2, the point of interest, 2, the value of interest, is on the left end of the interval, right? And what we're again trying to convey, like it doesn't make any difference. As long as 2 is in the interval that you use to compute the average rate of change is valid. And as you're seeing, just as with the previous example, these values likewise are also approaching 12, right? So it seems like we're getting the same value if we shrink the interval this way. And then in part C, now we're using symmetric intervals again, right? So now 2 is smack dab in the middle of each interval, but it doesn't matter. Like we're gonna get 12 again. We're gonna see a sequence of values converging to 12. F of 2.01 minus f of 1.99. And then finally f of 2.001 minus f of 1.999 over 2.001 minus 1.999. That is extremely close to 12, right? That's pretty convincing evidence that, in fact, the true value is 12. But if you wanted to be really sure about it, because after all, these are just estimates, you'd have to compute a limit. And we'll talk about that during the first days of the course. Okay, cool. So that's part 4. Finally, the last part of this packet, I don't think this is as long as it looks. It's just like there's a lot of pictures, so it takes up a lot of space. I actually don't think it's a very long section. Okay, so this is the first time I'm actually seeing these exercises, so I'm just kind of doing it off the cuff. Okay, so we want you to have a ruler, and we want you to have Desmos. I don't have a ruler, but whatever. I'm decent on the trackpad. So here we're just reminding you about the 3 standard like equations of a line. I gotta tell you, this form, standard form, it sucks. Like it's not useful. You'll never use it. These two, point slope and slope intercept, those are good. And actually, surprisingly, this one, which like for most of your life has probably been kind of like, you know, the odd one out, the one that you never use, that one, point slope, is the one that we'll use the most in this course. It's actually the most useful. But standard is just crap. It's terrible. Nobody likes that one. Anyway, write the equation of a line in any form that contains the points 2, 5, negative 6, 8. Yeah, I mean, I don't know. There's lots of ways that you could do this. I mean, I think that when you're given 2 points and you want to find the equation of the line, I think it's easiest to write down point slope form. This guy right here. I mean, after all, for point slope form, you need 2 things. Which 2 things do you need? Well, it's in the name. Point slope. You need a point on the line, and you need the slope of the line. Well, we definitely have a point on the line. As a matter of fact, we have 2 of them, right? So that's taken care of. But we also need the slope of the line. How do you find the slope? It's basically rise over run. Like you can think of it like using this formula. It's like change in y over change in x, but that's basically just rise over run. So, which point is like, so we can say that this point is x1, y1, and this point here is x2, y2. You could do it the other way around. It doesn't matter. Like you'll get the same answer as long as you're consistent about it. So y2 minus y1, that's 8 minus 5 over x2 minus x1, that's negative 6 minus 2. So that's 3 over negative 8. So that's our slope. And so going to point slope form, y minus y1, m, that's the slope, which I just found. And x1 and y1, those are the coordinates of whatever point you want. I decided to call this x1, y1, but you could also call this x1, y1. Doesn't make any difference. You'll get an equation which looks a little bit different, but it's going to be equivalent. So y minus 5, that's y1, equals m, which is negative 3 over 8 times x minus x1, which is 2. So there you go. That's point slope form. 33b. Find the slope of the line. Easiest way of doing this is to just put it into slope intercept form. So in other words, solve for y. So I'll subtract 5x from both sides and then divide by 4. And comparing this to slope intercept form, I can see that m is negative 5 over 4. So that's your slope. C, find the equation of the line that runs parallel to the line blah blah blah, but which shares the same y-intercept as blah blah blah. Okay. Well, so the fact that our mystery line, is parallel to this line means that our mystery line has the same slope as this line. This line here is in point slope form, and if I compare it, I can see that the value of m is 6. So the slope of this line is 6. Since our line is parallel to this line, that means that the slope of our line is also 6. So I'm just going to write m equals 6. Cool. What else do I know? I know that our mystery line has the same y-intercept as this guy. Well, what's the y-intercept of this guy? Well, if you put this equation into slope-intercept form, which actually I did earlier, it's right here. If you put that equation into slope-intercept form, this value right here, that's your b value, that's the y-intercept. So I know that my mystery line has a slope of 6, and it has the same y-intercept as this guy. In other words, it has a y-intercept of 5, so b, your y-intercept is 5. Well, okay, I know the slope of my line, I know the y-intercept of my line. With that information, I can write down the slope-intercept form of my line, which would be y equals 6x plus 5. So that's the equation. 34. Now go to Desmos. Done. And graph y equals x squared. They say y equals x squared. It's a good practice, as I said earlier, to not just type y equals x squared, but to actually give your functions names, like call it f of x, because then you can quickly do stuff like, what's f of 5? It's 25. Okay, so it's a good habit to just name your functions. Don't just call it y. So now go to Desmos and graph in the first line and 1, 1 in the second. Okay, so we're just highlighting the point 1, 1, which is right here. Maybe I'll put this on high contrast. There we go. Cool. I'm going to do something else. I'm going to get rid of minor grid lines and make a step of 1, 1. There we go. That's just how I prefer to view this guy. Okay, so there we go. So it says we started off with a nice curvy parabola. What shape does it kind of look like you're seeing? Oh, it says zoom into the point a few times, right? So I'm just going to zoom into the point. Okay. Oh, there it is. That looks pretty nice. Let me actually make this a little bit bigger to make it more prominent. That's not it. There we go. Yeah, so here it is. It says zoom in, right? After you zoom in repeatedly, what does the graph start to resemble? Looks like a line, right? It looks like a line. Okay, now it says use the grid to find the slope rise over run at 1, 1 of this almost line. I mean, it's not actually a line, it's actually a curve, but you zoom in enough, it looks flat, right? So I've got my grid here, and actually I've got some, the line almost goes through these grid points here. It's very close. So I think what I'm going to do is I'm just going to compute the slope from here to here. So what is that slope? Well, right here it's like 0.949 comma 0.9. Let me just write this down. So I'm going from, what is it, like, I'll just say 0.95 comma 0.9. That's good enough. 0.95 comma 0.9. All the way up to this point here, which, as we know, is 1 comma 1. And we want to know what's the slope of this almost line. It's not literally a line, but it's very close. So, if I just do rise over, sorry, this is number 35 here. So if I just do rise over run, that's going to be 1 minus 0.9 over 1 minus 0.95. That's 0.1 over 0.05. 0.1 over 0.05, that's 2. Which I guess was obvious, but whatever. So, yeah, so the slope appears to be 2 here. Okay, so that's pretty interesting. The slope appears to be 2. If you want it to be, now, I mean, that's kind of an estimate. Maybe you're worried that we estimated badly. If you were worried that we estimated poorly and you wanted a better estimate, all you would do is zoom in more. Like, if you zoom in really far and you pick like this point right here, that's going to give you an even better estimate of the slope at that point. Okay, so anyway, so sorry, that was not 35, that was 34. Okay, so 35. We're doing the same thing at 3 comma 9, and we're trying to figure out what is the slope at 3 comma 9. So let me just change this to 3 comma 9. I'm going to zoom out so I can actually find that point. It's up here. And, it already almost looks like a line. If I zoom in further, it looks exactly like a line, right? I mean, it's like super flat. So what is the slope of this line, approximately? I mean, I can just click on a point and sort of write down the values. So what is this? This is 2.999332, comma. How do I wish I could make that point stay on here. Okay, who is this? This is this is easy to remember. This is 2.995 8.97. Let's just use that. So So that's 2.995 comma 8.97 to r point 3 comma 9. Right. So if I look at the slope there, that would be 9 minus 8.97 over 3 minus 2.995, which is, let me just do it in Desmos. Oh, it's 6, exactly. Cool. Looks like it's 6. And then, yeah, repeat one more time. I'm going to skip to the chase. You should get -4 here. Okay, I think you should get -4. Yeah, do you see the pattern? So, here, when the x value is 1, the slope appeared to be 2. Here, when the x value is 3, the slope appeared to be 6. And here, although I didn't do it because I'm getting kind of lazy, the x value is -2, and the slope appears to be -4. It certainly seems like the slope is always just twice the x value. So my assumption here, for number 36, based on this pattern that I was just talking about, I think it's just twice the x value. So at x equals 5, the slope is probably 10. And then for -11, it's -22. And then at x equals 0, it's 0. And then at an arbitrary general point, x equals a, it's probably 2a, right? It's always just twice, okay? So here we have a bit of information about language. It says we define the slope of a curve at a point to be the slope of the line you see if you zoom in repeatedly. So math people would say the slope of y equals x squared at x equals 3 is equal to 6. Well, technically we haven't proven that, but it sure looks like it's really close to 6. More often we use the word derivative instead of slope. Much more on that word to come. For now, just treat it as a synonym of slope. We'll also say things like the derivative of y equals x squared at x equals 3 is 6. So basically derivative means slope, pretty much. Okay. Do I feel like doing this? I guess I should. I guess I should do this. What is this problem about? Write the equation of the line that passes through 1, 1 with slope 2. Okay, for that I'm going to use slope intercept form. Or, point slope form. So my point is 1, 1 and the slope is 2. So y minus 1 equals 2 times... Oh, it says use slope intercept form. Why? Ugh. Why? Why do I want to do that? Fine. Okay. Well, I'll start in point slope form. Right? So that's what it is in point slope form. And then to put it into y equals mx plus b form, I just need to solve for y. If I distribute the 2, I get this. If I add 1 to both sides, I get y equals 2x minus 1. Okay? So that's y equals mx plus b form for this guy. Cool. All right, so that's done. Go back to Desmos and type the equation you found in part A. Zoom in once around 1, 1, and notice both the curve and the line. Zoom in and again. What do you notice? I guess we'll find out. So let me reset this. So y equals 2x minus 1. Wait, what am I doing? Am I graphing this? Yeah. Well, here's the thing. So let me just make sure I know what the question is asking here. So the original graph that we're looking at here, y equals 2x minus 1, is already a line. And so you don't need to zoom in for it to resemble a line. It already is a line. And so if you zoom in again and again, the line that you're seeing is actually just the original graph. Do you see what I'm saying there? Most graphs, of course, are curvy, and for them to resemble the line, you would have to zoom in very closely, and eventually that curvy graph will look straight. However, if your original graph is already a straight line, those two notions coincide. The original graph and the line that appears when you zoom in are the same object. Okay, I suppose that's the point of this question. Line and curve. Wait, what? Oh no, I think what they're getting at. I see. What they're getting at is that this line right here is the line that we were seeing earlier when we zoomed in on this point. That's what they're saying. That's what they're saying. So initially, as you can see, here's the graph of y equals x squared, and then here's this line. But what we're claiming is that this purple line here, 2x minus 1, is the line that you begin to see when you zoom in on x squared a lot. So if I zoom in, zoom in, zoom in, as you can see, they start to overlap. Okay, that's the point of this exercise. I feel like that question could have been written a little more clearly, but whatever. Yeah, and then C and D are the same thing, right? So write the equation of a line that passes through, right? So this would be y minus 4 is equal to negative 4 times x plus 2, and then we're considering the point negative 2, 4. Right, that's the other one of the other points at which we computed the line, right? And so what we're claiming is that this blue line right here, that is the line that you begin to see if you zoom in on this point sufficiently far, right? So if I zoom in on this guy a whole bunch, you'll see that they start to coincide. So that's the point, right? Language here. These are tangent lines, okay? So this line right here is tangent to the curve because it just like nicks the curve at that point, like it just touches it, just goes through that one little point. And it gives us yet another way of finding slope, right? So what they're asking you to do here is, so this is number 38. Use your calculator on this point right here and try to make, I think I said calculator, not ruler. Drop your ruler right here and try to make it look like the tangent line and then estimate the slope. I don't have a ruler, but I do have like a line tool that I can use, I think, somewhere. Yeah, here we go. So I'm just going to pretend this is my ruler. I'm going to position it. Okay, that's not what I want. I'm going to position it so it's going through that point, but I'm just going to try and make it so that it's like flat up against the curve, like just nicking it, like that's pretty good. Something like that. I mean, this is kind of an estimate, right? Like I'm estimating what the tangent line looks like. It's very difficult to know for sure exactly what the tangent line looks like, but basically it should be going through that dot. It should be going through point A. Let me make this a little thinner. It should be going through point A, and it should be like just flat against the curve, right? Just flat against the curve, just touching it. And this line looks pretty good, okay? And if we wanted to find the slope of the curve at this point, it'd be pretty easy. We just have to figure out the slope of this line right here that we've just sketched, okay? And how do you find the slope of this line? Well, you kind of just look for grid points that the line almost goes through, like the line almost goes through this point right here, which is 0, 1. And then it looks like it almost goes through this point right here, which is 11, 4. So like, I assume they want us to find the slope of this line at some point. So 0, 1 to 11, 4. what's the slope of that line? That would be 4 minus 1 over 11 minus 0. So that's 3 over 11, which is about 0.272. So that's an estimate of the slope of the tangent line at this point. In other words, that's an estimate of the derivative of the function at this point. Okay. Anyway, yeah, so we're giving you some tips on how to place your ruler here. And then finally, what is the slope of the black tangent line? In other words, what is the derivative? As I said, I got about 0.272, but you're probably going to get something a little bit different, right? Because your line is going to be, just to emphasize here, like, this is a process of estimation, right? Like you're estimating the tangent line. Your positioning of the ruler is not going to be identical to mine, and you're also estimating the slope of the line that you've drawn. You know what I mean? Because like your line is not going to go perfectly through any grid points. So when you're trying to find points on the line, it's like, yeah, the line here seems to maybe go through this point, but it's probably not going exactly through that point. Maybe it is, but it's hard to tell. So there's a lot of estimation, okay? So as long as you get something sort of in the ballpark of this, you're fine. All right, but don't worry too much about like, oh my God, did I get it close enough? Don't worry too much about that. That's not really the point of these exercises, okay? So that's 39. All right, let's talk about number 40. Use this tangent line method to find the slope of y equals square root of x at 1. So use a ruler to sketch. Okay, so we're going to find the slope to the slope of y equals root x at x equals 1. Or put another way, we're going to find the derivative of this function at x equals 1. So what I want to do is I just want to look at the graph. I want to think about this point right here. That is the point on the line at x equals 1. And I want to create a line going through that point, but which is tangent to the curve. So I just want to go through that point, but just kind of have it like flat up against the curve. That's not very good. More like this. That's pretty solid. Maybe a little bit more like that is probably in the ballpark. Something like that. You do not have to be this precise. Like I'm able to be very precise because I'm using a computer. You do not have to be this precise. So what's the slope of this line? Well, it looks like it goes through this grid point here, and it looks like it goes through that grid point here, more or less. So that's a rise of 4, and it's a run of 8. So 4 over 8 looks like it's 1/2. But again, like you'll draw a different line, and you might use different grid points to estimate. You absolutely might not get 1/2. You might get something else, and that's fine. Estimate the slope at x equals 9. Yeah, same thing. Here's the point on the graph at x equals 9. I'm going to do my best to draw a tangent line going through that point. So something like... that's pretty bad. Still pretty bad. Yeah, that's pretty good. That's solid, I would say. Yeah, something like that. Okay, so what is the slope of this line? Well, it looks like it goes through this point, which is which is negative 1, 1, and it certainly goes through this point, which is 9, 3. So what is the slope? What problem is this, by the way? This is 40b. All right, so 40b. So we're going from negative 1, 1 to 9, 3. So what is the slope? That would be 3 minus 1 over 9 minus negative 1. That's 2 over 10, so 1 over 5. So about 1/5, right? About 0.2. Something like that. Yeah, right? Like over 10 up to... yeah, cool. Again, you'll get something a little bit different, most likely. Okay, So, all right, so number 41, we're going to find the derivative of this crazy function using two methods. Steps are below. One, we want to zoom in on this guy. And then two, we're going to use a ruler. And either way, we want to estimate the derivative of this function at x equals 1. So let me just clear all this other stuff out from the earlier problems. So I've got the function negative x cubed plus 4x squared minus 2x plus 1. And I'm interested in the point 3, 4. And I would like to find the slope of the line, of the tangent line going through that point. In other words, I want to find the derivative of this function at x equals 3. So method A is to just do what I just did and zoom in on this point. And hopefully I can sort of estimate like what the slope is. So here, the graph is definitely beginning to look like a line. What is the slope? Yeah, it's kind of hard to tell, you know what I mean? Because it's, I would really love another grid point here. I'm just going to ballpark it. Like, I'm not going to be too precious about getting it exactly right. The line more or less goes through this point right here, which is like halfway between 3 and 3.05. Like, I know it's definitely not exactly through that point, but like we're estimating, so whatever. So 41A, it's going through the point 3, 4, and then it's going through more or less this point right here, which is halfway between 3 and 3.05. So that's 3.025 is the x coordinate, and the y coordinate I can see is 3.85. So what would the slope be? The slope would be 3.85 minus 3.025 divided by, 3.85 minus 4 divided by 3.025 minus 3. So that's negative 6, but it's actually, I'm surprised that we got exactly negative 6. But yeah, it's probably not exactly negative 6. That's an estimate, but whatever. Okay, alternatively, we can look at this graph. We can mark 3. So this is method B. Mark 3, 4 right here like this. And then just like do our best to draw the tangent line through that point. So it's going to be pretty steep. Okay, hold on. Let's not go crazy. This must be truly riveting to watch. Yeah, something like that. Good enough. Whatever. Okay, so what is the slope of this line? Well, from here to here, between these 2 points, it looks like it goes down 5 over 1. So like negative 5. Like negative 5. So 41b, I'm saying that the slope is negative 5. As you can see, that's like obviously different from what I got here. This is an estimation. I don't actually know what the slope is. So anyway, estimate the derivative using the method of your choice. They're just saying, like, I don't know, pick one of these two values. Either one is fine. So the slope is like either negative 5 or negative 6 or something in between those two things.